conversation with Lisa Randall, a theoretical physicist and cosmologist at Harvard. Her work involves improving our understanding of particle physics, supersymmetry, baryogenesis, cosmological inflation, and dark matter. This is the Lex Friedman podcast. To support it, please check out our sponsors in the description. And now, dear friends, here's Lisa Randall. One of the things you work on and write about is dark matter. We can't see it, but there's a lot of it in the universe. You also end one of your books with a Beatles song quote, "Got to be good looking because he's so hard to see." What is dark matter? How should we think about it, given that we can't see it? How should we visualize it in our mind's eye?
I think one of the really important things that physics teaches you is just our limitations, but also our abilities. So the fact that we can deduce the existence of something that we don't directly see is really a tribute to people that we can do that. But it's also something that tells you you can't overly rely on your direct senses. If you just relied on just what you see directly, you would miss so much of what's happening in the world. And we can generalize this, but we're just for now to focus on dark matter. It's something we know is there. And it's not just one way we know it's there. In my book, Dark Matter and the Dinosaurs, I talk about the many different ways, there's 8 or 9 that we deduce not just the existence of dark matter, but how much is there. And they all agree. Now, how do we know it's there? Because of its gravitational force. And individually, a particle doesn't have such a big gravitational force. In fact, gravity is an extremely weak force compared to other forces we know about in nature. But there's a lot of dark matter out there. It carries a lot of energy, 5 times the amount of energy as the matter we know that's in atoms, etc. So you can ask, how should we think about it? Well, it's just another form of matter that doesn't interact with light, or at least as far as we know. So it interacts gravitationally, it clumps, it forms galaxies, but it doesn't interact with light, which means we just don't see it. And most of our detection, before gravitational wave detectors, we only saw things because of their interactions with light in some sense.
So in theory, it behaves just like any other matter. It just doesn't interact with light.
So when we say it interacts just like any other form of matter, we have to be careful because gravitationally it interacts like other forms of matter, but it doesn't experience electromagnetism, which is why it has a different distribution. So in our galaxy, it's roughly spherical, unless it has its own interactions. That's another story. But we know that it's roughly spherical, whereas ordinary matter can radiate and clumps into a disk. And that's why we see the Milky Way disk. So on large scales, in some sense, yes, all the matter is similar in some sense. In fact, dark matter is in some sense more important because it can collapse more readily than ordinary matter, because ordinary matter has radiative forces, which makes it hard to collapse on small scales. So actually, it's dark matter that sort of drives galaxy formation, and then ordinary matter kind of comes along with it. And there's also just more of it. And because there's more of it, it can start collapsing sooner. That is to say, the energy density in dark matter dominates over radiation earlier than you would if you just had ordinary matter.
So it's